it looks like it stopped. I apologize. I'm trying to do better every week in placement of the camera and the completeness of the videos. The YouTube channel has videos. What I'll do is if we miss something here, I will create a little supplement video, where you won't see me walking around, but I will show the same slides, and you'll hear me talking about it. So I'm glad I checked, because the camera sometimes, I don't know, it gets warm, it doesn't know what to do. Okay, so COBE, WMAP, and Planck, here they are on a curved surface. I like this presentation. You can see the COBE part over here. You don't get any spatial detail from this. I mean, you get the big stuff, but any kind of detail is missing. Here's WMAP, this band here, and then here's Planck. So, let's talk now. I'm going to say some things that we covered earlier, maybe in the first lecture, how we get the cosmic microwave background. Early universe, no atoms, just fragments flying around because the temperature was so high. And we have cooling until 380,000 years. Around there, we have condensation of those particles, those fragments, and produce mostly hydrogen. Almost 99% of the universe that formed at that time had nitrogen in it. And the important thing is, when that happened, the universe became transparent. Up until that point, this debris flying around, it was like going out in a fog and trying to take a picture. Because a light particle trying to propagate to your camera or whatever would have immediately got bumped into something and got scattered, and you can't take a picture that way. You can't visualize anything through a fog, but as soon as that fog cleared, now the light produced at that time now can travel in a straight line for the rest of the life of the universe. And that transition happened at 380,000 years. So this cartoon depicts that transition from the opaque, fragmented situation. We have this recombination, and now we have atoms, and light can propagate in straight lines, which is great because now when we look at the sky, at the wavelengths where the microwave background exists, we're seeing light coming from wherever it was created, and it's uninterrupted on its path to us, unless it encountered a star along the way. So, right now, the temperature we see is about 3 Kelvin, just above absolute zero, and we can infer from that, and the age of the universe we get from looking at galaxies and calculating Hubble's constant, we can infer that the light we see now in the microwave background was created when the universe was 3,000 Kelvin. So Herman and Alford got that wrong. But 3,000 Kelvin is kind of like in the ballpark of the surface of the sun. When we look at the sun and take its temperature, we get 6,000 Kelvin. Actually, 5,800 Kelvin. Okay? The interesting thing is, in the early universe, also there were sound waves propagating. The universe was so dense that sound was propagating back and forth in the universe. We're going to experience this during this lecture. So it looks like this, that when the universe was forming, pressure waves could propagate. The universe was much denser than, say, well, dramatically more dense than metal. If you take an iron rod and tap one end, sound propagates faster than it does in air, because the atoms are in intimate contact in solids. Well, the universe was dramatically more condensed than that, so sound can propagate. The interesting thing is that sound would propagate in one direction, and while it was propagating, the universe was getting bigger. So the sound would go over here and reflect, and by the time it was on its return path, the universe it was traveling in was dramatically bigger. So we have these oscillations where the side, imagine this, if we have any guitar players, imagine this situation. You pluck the guitar string, and while the waves are moving in the string, while the string is vibrating, the guitar gets dramatically bigger. So the tone you tried to create, when you pluck the string, might have occurred for a short time, but then soon the dramatic size increase in your guitar changes the tone. So this cartoon is trying to depict here waves propagating here and again here, but time has gone by, and this stretching has changed the pitch of the sound propagating in the universe. So if you were here, you would have heard loud noises. So here's our summary. We had this, or the beginning of the universe. This is the interval during which there were no atoms here. It's just random debris until this point. That's 380,000 years. And it only took, apparently, a very short time for the universe to go from being foggy and not able to support light traveling to becoming transparent. A few thousand years, maybe. Then we have a dramatically longer interval. Here it says 300 million. Most people say 400 million years where the universe was transparent and dark, because there were no stars. And it wasn't until 400 million years we get the first stars, and then we get collections of stars and beginnings of galaxies. And so the interval of darkness is this band right here. And galaxies. And this, there was a source of light. It would have been visible had you been there to observe it. When the universe became transparent, the only light around was what we now see as the cosmic microwave background. And it wouldn't have been microwaves, it would have been a bright light. So, what does this tell us? What does the distribution of these variations in temperature across the sky tell us? I mentioned this is, to me, one of the most important science pictures ever taken. And it has to do with the spatial distribution. When we look at the sky, the separation between the cold and dark regions and the brighter blue regions, those tell us the geometry of the universe. And so these cartoons show you that if the universe was closed, that is, if the universe was spherical in shape, the light coming to us would have been confined to move on a spherical surface, and we would see a different distribution of galaxy clusters than if the universe is flat, which now appears to be what we're dealing with, or the so-called open universe. Open universe kind of looks like a saddle. It doesn't close on itself, and remember I showed you that, probably worth doing this again. On a flat surface, triangle has 180 degrees. On a spherical surface, you can draw, here's the equator, you can draw this, and this, these are both right angles. So there's 120 already, but then there's that angle there. So on a sphere, triangles can have more than 180 degrees. And this other shape I'm describing kind of looks like this in that direction, and this in this direction. So it looks like a saddle. Very hard for me to draw it. And here, triangles have less than 180 degrees. So the distribution of these bright, warm spots and the cold, darker spots in the picture taken by the Planck spacecraft tells us the geometry of the universe. Remembering that, of course, the difference between warm, these red areas, and the cold areas is extremely tiny, a fraction of a thousandth of a degree. So this is a panel you can read at your own pace about what has to be done to remove the Milky Way influence. You got to do that right, otherwise this area, the equatorial area of the picture, gets distorted if you don't remove that influence properly. Because looking in the plane of the galaxy, our galaxy, you're looking at billions of stars. Many of them are radio sources that are right in the same wavelengths as the microwave background. So I want to emphasize this. When we look out, here's out in the distance was the Big Bang, which we can't see. But right here is the cosmic microwave background. And the light from that is propagating toward us. So we're, from our point of view, is we're at the center of everything. But every planet in the universe would have the same experience. We're at the center of everything. Just like raisins in the raisin bread, when you cook it, all the raisins appear to recede, and if they're sending you signals, it appears to you like you're the center. In fact, there's no center. The universe is expanding everywhere all at the same rate. So, when we look out and see the microwave background, or the earliest stars in this region, we've built ourselves sort of an onion, and we're at the center. And so what this depicts is, if you go out on a cloudy day, you don't get much signal from any light that's trying to propagate through clouds. You can't form an image with that, but when you have clearer weather, we can see them. Oh, good. Well, so here's our, let's redo this. Here's our closed universe. It would have this distribution of hot and cold on the sky. Here's the universe we think we have. We're going to talk about this more. That's the flat universe. And here's the open universe. Because of the shape of this saddle, the distant galaxies look like they're more compressed together, that they're all in proximity. So if we go back here, you can see this. This is the open universe. So an open universe would have this kind of trajectory for light from the different galaxies coming to us, and it looks like the variations are closer together. These spots right here, those guys, they're much smaller than these clusters of galaxies, this warmer area. So from the picture, we can infer the geometry. Now, we do need to talk about what they are actually measuring. So I've already mentioned that they're measuring black body radiation. Here's obviously a picture of Earth and Earth's temperatures in the equatorial regions, much warmer, very distinct. And we know why, of course. It has to do with solar heating and so forth. Here's our microwave temperatures. The blackest areas, the darkest areas are here at this temperature. These are centigrade now, minus 270.4252. And the brightest areas are minus 270.4248. So we're at 0.4 millikelvin. That's the difference. And so here's once again, here's the black body curve I sketched on the board. For a bright object, 7,000 Kelvin, like a star, has a peak here, near the shortest wavelengths that humans can see. That's this band. So this is blue through red. This is what humans can see. And a bright star has a peak in the blue. And if you're an amateur astronomer, you've probably gone out through a telescope or even binoculars, and you can see blue stars. They're the hottest, brightest stars. Cooler stars will have a peak here in the red. And then as you progress over here, you eventually can get to, well, here's my example. There's a human wearing glasses that have lenses made of plastic. So plastic won't convey the infrared radiation. And he's got his hand in some kind of a, I don't know if you can see that, it's some kind of a plastic bag, possibly. You can barely see through it. Here's the space shuttle landing. Nice and warm on the bottom, much cooler on the top. So, the peak of the curve tells us the average temperature of the radiation we are detecting. And even Penzias and Wilson got this pretty close. I think they measured something like 3.5 Kelvin from their ground-based antenna. Now, we come to sort of an abstract thing. This picture is useful. It tells us the temperature. But we can do more, because we can analyze this. We can analyze the distribution of warm and cold spots in the microwave background using mathematical techniques, and it ends up producing this. And this tells us where on the sky is where is the frequency highest of spaces between bright and dark. So if we go, let's go back and look. You can almost do this yourself just by eye. Let's get a nice picture here of the microwave background. Like right here. So you can kind of see, if you wanted to find what is the spacing of the coldest parts of this image. So you can say, well, this difference, remember these are angles because we're looking at the sky. This one, and this one, and this one, and this one, they're all about the same distance apart. Then there's some, like these two and that one, where they're much closer together. And then there's some where this one and this one are farther apart. So there's this statistic you can do where you measure those differences and you add them up. And this curve that I just showed you, this tells us what is the angle that happens most frequently. And it's about 1 degree. And then there's some bumps, which are interesting. We can talk about those. This is how we make the next step in exploiting the images taken by the Planck satellite and its predecessors. The error bars represent measurements made from the ground or earlier experiments. You'll see how this has improved. Technically, people understood how to do this better. Here's an example of what we're talking about. This is the same curve I just showed you, plotted a little differently. Most of the spacing between cold spots or the warm spots is right around here. We don't have to worry about what that scale is. This is about 1 degree. Well, you can see it up here. So there's a 1/2 degree and there's 2 degrees. Right around 1 degree. That's a very common spacing for the variation. Now, what we're looking at is black dots come from the WMAP spacecraft. And then we have some measurements here that come from, these are all in the atmosphere or from the ground. And they're not as good because they're looking through the atmosphere, and that makes it harder. So that's what these vertical lines are. These are error bars on each of the measurements. But you can still see this kind of lumpiness, and we've drawn a nice smooth curve through the dots to try to make it sensible. Now let's look at, there's what we just showed you. WMAP and these ground-based, oh, by the way, this one is very interesting, Boomerang. That's an Australian, what a surprise, Australian experiment to measure the microwave background. And they do this very clever thing. They exploit the fact that at the South Pole, not far from Australia and New Zealand, there's a thing called a circumpolar vortex. So let me draw a I'm going to imagine I turn the Earth upside down. So this is the South Pole. There's a band of wind that goes around the South Pole persistently. It just goes around and around. It's called the vortex. So here's New Zealand and Australia. So what they do is they built an instrument like the one that's on the satellites, a microwave radiometer, put it on a balloon, and watch it from someplace in Antarctica up into the vortex, and it gets caught in the wind and it goes around the planet, reappears, they bring it down, and they get the data. So they get the instrument back, and they can fix it if they need to. And then when they're ready, they can launch it again, and it goes around. It takes, I don't know, 10 or 12 days to go around. And because it comes back, they need that boomerang, and it produces useful data, not as good as the data in space. So anyway, yes, sir?
Is there a similar vortex on the North Pole?
It's not as well organized. The circumpolar vortex at the South Pole is unimpeded by the influence of land masses. Right? It's just, the Antarctica is there, sort of centered on the pole, but north, if you go at the South Pole and you go northward, it's ocean. And it's kind of uniform in terms of the way that ocean interacts with the sun. The North Pole is different. As you go around, there's land mass up. There's no land mass above at the pole, but as you go down, it's complicated by parts of Alaska and so forth. So there's our picture now. This is what we get from Planck. All this confusion here, these error bars, look at this. It's like this curve is a nice depiction of what's going on out there in the distribution of temperature from the early universe. Remember, the light we're detecting came from 380,000 years ago. Sorry, stop. 380,000 years after the birth of the universe. That light has been going in all directions unimpeded by that cloudiness of the early universe. And look at the quality of this data. Now there's a reason it gets fuzzy over here. Let's go back. It's important that you understand this. It gets fuzzy here. Remember, this angular scale is going from tiny angles getting bigger going to the left. So when you get over here, let's use this drawing again. This used to be a drawing of our planet. It's the same geometry, so we'll keep using it. Now we're looking at the universe. If you're seeing this kind of structure that the cosmic microwave background has, we can measure that. You can concentrate on this little area here and get lots of data because there's a lot of structure on the small scale. But how about, can we find correlation between this spot and this spot? Well, there's only a few of those because the universe has a limited size and we only have one universe to work with. If you want to find the IQ of people in Fort Collins, you don't test 12 people, right? You test as many people as you can find, but when we're dealing with the universe, we only have one universe to look at. So it's not a surprise that the data is very fuzzy over here, because this is the angle that is where pieces are way far apart, and there's only so many of those way far apart places to consider. So, excellent data here, and this curve goes right through where we care about it. It goes right through the data points. But now I've been keeping a secret. You see this? The data, the line that goes through the dots, it's not just there because we did statistics. It's the prediction of inflation, the inflationary theory of the early universe. Once you pick a couple of numbers, the data goes right through the points. This is why early in this lecture I mentioned the quality of our ability to predict the gyromagnetic ratio of the electron. We can predict it to 11 digits and we measure it to 11 digits, but we still don't really know what nature is doing. But we have a model that matches the data. It was conjured up by a guy, Alan Guth, who's still working at MIT. And his theory has